Good morning. All right, so we're going to finish up 4.6 today. Tomorrow we will go through the practice test for Chapter 4. Don't forget the test will open at midnight tonight, though. So if you want to get started on it, and actually do it tomorrow before our review, that's perfectly fine. But if you want to wait until after the review, we will do the practice test tomorrow, and then you can find a time, after that, between then and Friday, to actually do the test, because the test will be due at midnight on Friday. Also, don't forget that the 4.5, 4.6 homework is due Friday by midnight. So if you haven't finished that one up yet, just make sure you're working on that. Okay. Next week, we will do Chapter 10. Like I said, I don't have to cover the entire chapter. So I will do, as much as I can of that unit. I'm going to go ahead and just post the test pretty much at the beginning of the unit. So beginning of next week. And just give you the entire week to work on it. So you'll turn it in at the end of next week. Again, you won't need to do that one in Respondus. You can actually just do that on your own time. Use your notes, use your book, whatever you want to, and then you can just submit that on Friday of next week. Okay, so that's the plan for Test 5. And then if you haven't seen already, I did post an announcement with a survey link. So that's for you to sign up for an exam time the first week of May. So make sure that you go ahead and do that, because I do need those responses by Friday of next week, just so I know when people are planning to take their final exam. And like I said in there, basically, if you don't sign up for an exam time, then I'm just going to assume that you're not planning to take the final, and you'll just get a 0 for the final. Okay, so just make sure you get in there and sign up for an exam time whenever you get a chance. Okay, I think that's all in terms of announcements. Any questions, comments, concerns before we get started today? Absolutely, yeah. So just if you need to change your time, just email me to let me know. But at least go ahead and try to sign up for a time that you think will work. But yeah, just try to let me know as soon as possible if you need to change the time. Okay. Any other questions? All right. So we started looking at exponential models yesterday, right? And so we're going to continue that today. So example 2 here, we've got a certain breed of rabbit introduced onto a small island 8 months ago. The current rabbit population on the island is estimated to be 4,100 and doubling every 3 months. We want to know the initial size of the rabbit population. All right, so first off, all right, what formula are we going to be using in this case? So what type of problem do we have here? It's doubling time, right? Okay, so notice here, we've got the keyword doubling, which tells us we're going to use that doubling time formula that we looked at yesterday. So that was n of t equals n sub 0 times 2 to the t divided by a. Okay, so remember, n sub 0 is our initial population, 2 is because it's doubling, right? And then t is our time, a is the doubling time. So first thing we want to do is create the model that we're going to use so that we can actually find what we're asked to find here. Okay, so what information are we given this time? Okay, good. Our A value, our doubling time is 3 months, right? So we know that for sure. We're going to have something times 2 to the something over 3. Okay. What else do we know? All right, good. We're given here that we introduced this rabbit population 8 months ago, right? So at this point, our time is 8 months because 8 months has actually elapsed. So we're going to say t is equal to 8. Okay, what else do we know? Okay, good. The 4,100 is the current population, right? And we're looking for the initial. So we're actually looking for n sub 0 this time, but we know that after 8 months, our population is up to 4,100. Okay, so that's how we're actually going to set this one up this time. So notice this is different from example one, because in example one, they told us how much we started with. This time we're looking for how much we started with. Now, how would we find that initial population based off this formula now? Okay, good. We're just looking for n sub 0, right? So how would I get n sub 0 by itself at this point? Yeah, we can just divide, right? So 2 to the 8 thirds, that's just a number. So I'm going to divide this side by 2 to the 8 thirds. And I'm going to come over here and do the same thing. Okay, so just be careful when you put this into the calculator. Just make sure that 8 thirds is all in the exponent group together, right? But if we do 4,100 divided by 2 to the 8 thirds, what should that give us? All right, so we get n sub 0 equals 645.7, right? Just that's what we get in the calculator. Now, what is this referring to? What would our units be? It's rabbits, right? So do we want zero point 0.7 rabbits? No, we don't, right? We always want whole numbers of rabbits, preferably, right? So in this case, we're going to need to round. Now, it's kind of a gray area about which way you should round. You know, some people say always round up, right? If it's 0.5 or above. In this case, technically, because we haven't reached the 646th rabbit yet, we actually, because we're dealing with whole rabbits, would probably want to round this down. And so, you know, the book says 645. If you did 646, I'm not going to take off points, right? Okay, but in this case, because we haven't yet reached the 646th rabbit, we would actually probably want to round this one down to 645 rabbits instead. Okay. All right, so that was the number of rabbits. That is our initial population this time. Any questions about how we got that now? All right, so now we know the model, right? Because we have our n sub 0. So our function then is n of t equals 645 times 2 to the t divided by, 3. All right, so now the second question is we want to estimate the population 1 year after the rabbits were introduced to the island. So how are we going to find that? Good, right? Since our time here is measured in months, we have to think about 1 year as months. So we're going to say that t equals 12 for 12 months. And we're just going to plug that in. So we're going to get n of 12 is equal to 645 times 2 to the 12 over 3. And at that point, right, if you want to put all that right in the calculator, you can. If you want to simplify it, you know, step by step, that's fine too. This one simplifies pretty nicely. 645 times 2 to the 4th. 2 to the 4th power should give us 16. And if we do 645 times 16, what would that give us? Good. 10,320. And again, this is a population of rabbits. So our units here would be rabbits. Any questions on that one now? Okay, now I'm not going to do the sketching the graph piece. Just real quick though, what would this graph look like? What shape would it be? It's a J-shaped curve, right? So in this case, our initial is 645, so that would be our y-intercept. It's going to be J-shaped because our base is bigger than 1, and so it's going to be this exponential growth model if you were to actually put it in Desmos. All you'd have to do, though, is just replace the t with an x, and you could actually put this in Desmos and see what the graph looks like, okay? So if you're ever asked to graph one, you can just use Desmos there. All right. Now, if instead of looking at doubling time, excuse me, we're given a relative growth rate instead, then we can use this formula. Okay, so if a population that experiences exponential growth increases according to this model, our R value now is the rate of growth. Excuse me. Everything else stays the same. N sub 0 is the initial population. T is still time. The only difference now is because it's not doubling ever so often, okay, we actually have a growth rate. We're going to use that instead. And just like with interest, we're always going to convert that into a decimal, right? If they give us a percentage, and we're going to plug it in. Now, look at this formula. What does this formula look like? What is it very similar to? PERT, right? Okay, so the only difference now is instead of a P, we're using N sub 0. P is an initial amount of money. N sub 0 is an initial population. So instead of talking about money, now we're talking about numbers of things, right? But that's the only difference. We're still using that PERT formula just with numbers of populations, okay? So if you know your PERT formula, you should know this one now, right? Because we're just starting with things instead of money. All right. So the initial bacterium count in a culture is 500. A biologist, that should be later, makes a sample count of bacteria in the culture and finds that the relative rate of growth is 40% per hour. So we want to find the function that models the number of bacteria after T hours. So in this case, because we're given a relative rate of growth, that tells us we're going to use this other formula instead of the doubling time formula. All right, so what do we know in this case? All right, good. So our N sub 0 is going to be 500, right? That's our initial count of bacteria. What else are we given? Good. Our R value now, we always want to convert that to a decimal. That's going to be 0.40 or just 0.4. So now we have everything we need to actually write our model, because this is going to be N of T equals, we start with N sub 0, so we're going to have 500. Our base now is going to be E, and we're going to raise that to the R times T, so that's 0.4 times T. Any questions about finding the model this time? All right. So now we want to know the estimated count after 10 hours. So how are we going to find that? Good. T equals 10, right? So that's our time now. We're going to plug that in. So we'll find N of 10. We got 500 times E to the 0.4 times 10. Now, in this case, right, I would probably just put all of it right in the calculator. If you want to multiply the 0.4 times 10 first, so that you can just put 500 E to the 4th power in there. Okay, but you're going to have to use the calculator, right, because E is just an irrational number. So if we do 500 E to the 4th power, what do we get? Good, right? So 27,299. And in this case, right, again, I would round to the nearest whole number, right? Because we are talking about a number of bacteria. So 27,299 would be the number after 10 hours. Any questions about that one? All right, and then if we want to know after how many hours the bacteria count is going to reach 80,000, how are we going to set that up? Okay, good. Set our model equal to 80,000, solve for t. So we're going to have 80,000 equals 500 e to the 0.4t. So what's going to be our first step then if we're solving for t here? Good. We're going to divide both sides by the 500. What is 80,000 divided by 500? Good. So we get 160 equals e to the 0.4t. Right, then we can do what? Good. And in this case, what kind of log would we want? We want to use natural log, right? Since the base is e on the right-hand side, let's go ahead and use a natural log on both sides. So I have natural log of 160 equals the natural log of e to the 0.4t. So what's that going to give us on the right-hand side then? Good. Just the exponent, right? Because natural log of e to that power should just give us the power. We'll get natural log of 160 equals 0.4t. And then we can do what? Good. Just divide. So we have natural log of 160 over 0.4 equals t. And at that point, I would go to my calculator, actually find a t value and round it off. So what is that going to give us approximately for the time in this case? Good. Okay, so 12.69. Okay, if you round that to 12.7, right, it doesn't tell us what to round to. Just pay attention in WebAssign because it'll tell you. Okay, so 12.69, and what are the units going to be this time for our time? In this case, we're measuring hours. So after 12.7 hours, we've reached about 80,000 bacteria. And again, I'm not going to do the sketching the graph piece, but if you wanted to, you could put this into Desmos. Again, it's just going to be 500 e to the 0.4x. You would see then that the y-intercept is at 500. So keep in mind, right, a lot of these are going to have pretty large initial values. So you're probably going to have to zoom out or adjust your y-axis to be able to see the graph. But this would also be that J-shaped curve because it's going to be exponential growth. Any questions on this one now? All right. Example 4. Okay, so now it says in 2000, the population of the world was 6.1 billion, and the relative rate of growth was 1.4% per year. It's claimed that a rate of 1% per year would make a significant difference in the population in just a few decades. So we want to test that claim by estimating the population in the year 2050 using a relative rate of growth of 1.4% and then a relative rate of growth of 1.0% instead. We're basically saying, okay, if we were to use these two different percentages, what would we estimate the population to be in the year 2050? And we'll see if there's a significant difference in using those, because they're only off by 0.4%, right, which is not a large amount. All right, so let's try this then. So how are we going to set up? Let's go with part A, the 1.4% per year. So how are we going to calculate what that population would be in the year 2050? What do we know? All right, so we can use our initial population as 6.1, and we'll just call it billions, right? So we can just use 6.1 there. Use our rate of growth here, R equals 0.014. If we move that decimal 2 places to the left, good. And we're looking now for the population in the year 2050. So what does that tell us? Good. Our time here is going to be 50, because notice we started in the year 2000. We're now in the year 2050. So 50 years have passed. So we're going to use 50 as our T. So now we're going to do N of 50 is equal to 6.1 times E to the 0.014 times 50. So that's our relative rate of growth formula, okay, with a rate of growth of 1.4%, number of years 50, and initial population 6.1 billion. All right, so if we solve this now, what is that going to give us as our estimated population in the year 2050? And we'll go with 2 decimal places here. Okay, so 12.28. Good. And then don't forget that this is billions of people now, right? All right, so that's what we get if we use the 1.4%. Now we want to do the same thing, but we want to do it with 1% instead. So now we're just going to change our rate of growth to 0.01. So again, we're looking for N of 50. This is going to be 6.1 still, E to the 0.01 times 50. So if we do this with a rate of growth of 1% instead, again, we'll go with 2 decimal places here. Good, 10.06. Again, that's in billions of people. All right, so is there a significant difference here in our population estimate if we go with 1.4% versus 1%? Yeah. I mean, I would say that, 2.25 billion people is a pretty significant difference in this case, right? So just notice here, it doesn't take much of a percentage difference to make a pretty large difference in your estimates if you're looking at decades out, right? So 50 years into the future, you can make a pretty significant difference just by being off, by 0.4% in your prediction of what the rate of growth is. So this is why it's so important that when scientists are making these predictions, that they're as accurate as possible in what those rates of growth are, because otherwise, and these are all predictions, right? So things change. Population growth either goes up or down, but this at least gives us an idea. But it's important that we're as close as possible. So you can see here, it just says to graph them both. What you would notice, obviously, right, is that one of them is going to start to grow at a much more steep rate, right, because of that rate of growth. So the further out you go, the farther apart these are going to get. So if you look even 100 years out, there's going to be a really significant difference between those estimates at that point. All right, example 5. Okay, so a culture starts here with 10,000 bacteria, and the number doubles every 40 minutes. Okay, so the first thing we want to do is use that doubling time formula to get our model based off of the information that's given here. Now, notice that we're given a doubling time in minutes, but we want our function to be in terms of hours. So what are we going to need to do first this time? Okay, we need to convert that into hours, right? So we're going to take 40 minutes. We're going to convert it into hours. We know there's 60 minutes for every 1 hour. Minutes cancel. So we end up with 40 over 60, which is what? What would that simplify to? Good, 2/3, right? So 2/3 hours is our doubling time this time, right? So that gives us our A value. But since we want this in terms of hours, okay, just make sure you always convert to the same units. So our T is in hours, our doubling time also has to be in hours. Now, I'm going to go ahead and substitute everything in that I know here. So we're looking for our model, N of T equals, what's our N sub 0 going to be? Good, 10,000 is our initial. Start with that. We're doing a doubling time, so that's going to be 2 as our base. Then we're going to do T divided by, and then what are we going to use for A this time? 2/3, right? So we're dividing T by 2/3. Now, we don't want to leave a compound fraction, right? So we got T over 2/3 here. What would T divided by 2/3 be the same thing as? Yeah, not T to the 3/2, but multiplying by 3/2, right? So we multiply by the reciprocal. So we're going to say T times 3/2. So our exponent now is actually just going to be 3/2 T. So whenever you divide by a fraction like that, just remember that's the same thing as multiplying by the reciprocal. And so our exponent just becomes 3/2 T instead of T over 2/3. Any questions on finding that model? All right. Now, the second part of this one is we want to actually write our model in a rate of growth model instead. Okay. So we've got to think about, in this case, we're not given the rate of growth, right? So we've got to find a way that we can find that, because that's the one thing we need in this case to be able to write our model. How could we set this up so that we could find that relative rate of growth? All right, so let's think about how we're going to solve for R, though. So what's our N sub 0? Let's start with that. Still 10,000, right? So our initial population, still 10,000. That's not changed. E is just going to be E. We know we're looking for R, but now we need a T value and an N of T value if we're going to solve this for R. What could we use for T and N of T to help us solve for R now? All right, we could let T be 2/3. Sorry about that. So if we do that, I'm going to multiply by 2/3. If I multiply by 2/3, what's my N of T value going to be? Why 20,000? That's the double, right? So we know that it doubles every 40 minutes. We started with 10,000. And so after 2/3 of an hour, after 40 minutes, we should be at double what we started with. So we should be at 20,000. So that's how we're going to set this one up now to be able to solve for our rate. So now how are we going to solve? What would you do first? Okay, good. Divide by the 10,000, so that's going to give us 2 equals E to the 2/3 R. Then we can do what? Good. Take the natural log of both sides. So we get natural log of 2 equals natural log of E to the 2/3 R. So our right-hand side now is just going to give us what? Good, right? Just the exponent, so just the 2/3 R. And then to get R by itself, we would do what? Go ahead and move the 2/3. So we're dividing. That's the same thing as multiplying by the reciprocal. So we're going to end up with 3/2 natural log of 2 equals R. And then at that point, right, I would actually convert it into a decimal. So go ahead and put that in the calculator, see what you get. I would keep 4 decimal places here just to be as accurate as possible. So we do 3/2. Okay, so what we're really doing here is we're dividing both sides by 2/3. But remember, just like before, when we divide by 2/3, same thing as multiplying by the reciprocal. So this just becomes 3/2 natural log of 2 now. Does that make sense? Um, so we're using 2/3 for our t value because we know that our time that it takes to double is 40 minutes, which is the same thing as 2/3 hours. And since we want our model to be in hours, I'm using that 2/3 hours as my doubling time and saying that it takes that long for my population to reach twice what it was to start with. Okay. Any other questions up to that point? All right, so what's our rate going to be now if we round this decimal to 4 decimal places? All right, so I got something slightly larger than that. Okay, so double check, just do 3/2 natural log of 2. I think you might have put 2/3 instead of 3/2. There we go. All right, so 1.0397. Okay. So that is our rate of growth now, right? So when we write our function, we're going to have n of t equals initial population 10,000 times e to the 1.0397 t. So that's going to be the function we would use now if we wanted a relative rate of growth model instead of the doubling time formula. Now, what's nice here, right, is that you can use either one of these formulas at this point because they're equivalent to each other, right? So we've basically taken the first one, rewritten it in this other form, okay? But these two models, obviously this one we rounded that decimal, so it's going to be off slightly, right? But they should be pretty much the same. If you were to choose a value of t and plug it in, you should get the same value for your population in either model. Any questions on that one now? All right, now radioactive decay, right? So far all we've looked at is exponential growth. Now we're going to look at what happens if we have something that decays instead. So if M sub 0 is the initial mass of a radioactive substance, again, that subscript of 0 just means at time 0, so that's our initial, with a half-life of h, then the mass remaining at time t is modeled by the function M sub 0 e to the negative RT. Notice here, the only thing that's changed compared to our other formula, we're still starting with an initial amount of something. We still have E as our base, R is our rate, time is T, but now we have a negative R value because we're decaying at a certain rate instead of growing at a certain rate. That's the only thing that's going to change in this formula now. Now, if we're given the half-life, the H value, then we can use this formula right here to go from half-life to rate of growth. Okay, so if you want this model right here, instead of using a base of 2, we want to use the base of E, we can calculate R by just doing natural log of 2 divided by our half-life. That will give us our rate of decay, and then we can just plug that in. All right, so let's take a look here. This will be the last one we do. So polonium-210 has a half-life of 140 days. We want to suppose that a sample of substance has a mass of 300 milligrams. The first thing we want to do now is find the two different models. We're going to do one that's half-life, right? That's the base of 2. And then we're going to do one that's the rate of decay, which is the one with the R value in it. All right, so if we start with this first model up here, M of T, what is our M sub 0 going to be this time? Okay, good. So our initial amount is 300 milligrams, so that's M sub 0. So we're going to start with that. We're going to use a base of 2 because we're doing a half-life, right? So this is basically, instead of doing 1/2 to the time, we're just saying 2 to the negative T over H, which is the same thing as using a fraction as our base, okay? Maybe this way we can kind of keep the form the same as the original doubling time formula. Then we're going to have negative T divided by, and then what's our half-life going to be? (140), right? So notice here, we want this to be in days. Our half-life was given in days. Right? So this is our H value now. Any questions on finding that model? Okay, so basically we're just saying M sub 0 is the initial amount, right? So that's the 300. The 2 is the base. You could, just so it's clear, right? You could actually write this as M sub 0 times 1/2 to the positive T over H instead. Those two equations are equivalent to each other. Okay, so it's up to you whether you want to use a base of 1/2 or a base of 2. If you use a base of 2, we just have to use a negative exponent. If you use a base of 1/2, then it would be a positive exponent instead. Right? Instead of doubling time now, we have what's called half-life because this thing is being cut in half every 140 days instead of doubling every 140 days. Okay, but again, these two models would be equivalent. So if you wanted to do this one, it would be M of T equals 300 times 1/2 to the T over 140. That's the only difference. Because remember, with a negative exponent, we can just move it to the denominator. And so that's why that 1/2 would then just become a 2 to the negative 1, right? Or a 2 to the negative T over 140 in this case. So you can write that in either form. But basically, 0 is initial, H is half-life. So in this case, it tells us that our half-life is 140 days. So that's how we got that value as H instead of T. The model itself is going to always have a T in it because we don't know what the actual amount of time is. Okay. All right. Right, so Emma, that's going to be the next model that we look at, right? So that's the M sub 0 e to the negative RT. So we're looking at both forms this time, right? So one form is using the half-life with the base of 2, and then we're going to look at how we can convert it to this rate of decay formula instead. Okay? So just like we did for doubling time and rate of growth, we also have a half-life formula and a rate of decay formula that we can write as two equivalent forms. Okay? All right, so now if we want to find this other form, M sub 0 is not going to change, right? T is still going to be in our formula, so the only thing we need to find now is R. Okay, but remember, we have this little shortcut where we can just do R equals natural log of 2 over H to find the R value. So that's what I'm going to use here so that we don't have to actually set this thing equal and solve it like we did the last one. We'll say R equals natural log of 2. And then we set our half-life as 140 days. So we'll divide by 140. So what's that going to give us as our R value then? And this time I'll probably keep 6 decimal places just because there's some zeros at the beginning of that decimal. Good, right? So 0.004951, that's our rate. And that's rate of decay this time. So we have M of T equals 300 times e to the negative 0.004951 times t. Any questions on how we got that model now? Again, if you were to graph both of these models, right, if you put them in Desmos and just use an X instead of a T, both of these should be equivalent, right? Are you asking about the natural log of 2, Callie? Yeah, so that was just from this formula on the previous slide. So we have natural log of 2 divided by H. That's how we're always going to calculate the R value. Okay. Any other questions there? All right, so now let's find the mass remaining after 1 year. Now, like I said, these two models are equivalent. It does not matter which one we use because we should get the same answer either way. So which one do you want to use first of all? All right, so the Merck formula, that works. Okay, so if we use the second one here, what are we going to substitute for T to find the mass after 1 year? Good, right? Remember, our T is measured in days here. So we're going to have to use 365 as our T value, since that's how many days would be in a year. So we're going to have M of 365 equals 300 e to the negative 0.004951 times 365. And again, I would just put all that right in the calculator. Again, just make sure your exponents group together when you do that. So we'll just go with 2 decimal places here. So if we round that to 2 decimal places, what's that going to give us? So 49.24. And then what are those units going to be this time? Good. So we're measuring this in milligrams. So we have 49.24 milligrams of that substance remaining after a year. Now, one thing I always encourage people, think about the problem, think about what you're actually talking about and make sure your answer makes sense. So in this case, right, we started with 300 milligrams. We know it's decaying, right, and it's going to be cut in half every 140 days. So after 140 days, we'd be down to 150. Then 140 days later, we'd be at half of that, which would be 75. And then another 140 days would put us at half of that, which is more than a year though, right? So we would have gone beyond a year once we reach half of 75. So we know we're somewhere between, in this case, that would be 37 and a half, and 75 would be, the doubling time, or sorry, the half-life twice and 3 times. So 49.24 does make sense. Okay, but if your number went up, then you did something wrong, right? Because in this case, we are decaying over time. So just make sure you're getting a value definitely smaller than what we started with. All right. And then the next question, this will be the last thing we do. How long will it take for a sample to decay to a mass of 200 milligrams? So how are we going to do that? Good, right? So set the formula equal to 200, and it doesn't matter, again, which one you do. So we'll use the second one here. So we'll do 200 is equal to 300 e to the negative 0.004951 t. And steps are going to be exactly the same as all the other ones we've done for solving for t. So what do we do first? Go ahead, divide by 300. What is 200 divided by 300? That's going to give us 2/3. So we have 2/3 equals e to the negative 0.004951 t. And then we can do what? Take the natural log of both sides. Good. So now we have the natural log of 2/3. And then if we take the natural log of the other side, remember that's just going to give us the exponent. So we have this. And then our last step is to do what? Good, just divide by that decimal. So if we do natural log of 2/3 divided by all of this, what's that going to give us for our time? And 1 decimal place is sufficient here. Okay, good. 81.9. And what are those units going to be this time? Good. Don't forget, our time this time was measured in days. So almost 82 days for our sample to get from 300 milligrams down to 200 milligrams. Again, this is one where you can kind of think, make sure your answer is reasonable. We started with 300. We know after 140 days, it should be half of that. So we haven't gone that long, right? Because we're only at 200 milligrams, not half of 300. So it's somewhere between 0 and 140 days. So 82 days makes sense. Any questions on that one now? All right, so like I said, just make sure you get the the 4.5 and 4.6 homework done by midnight on Friday. We will go through the practice test tomorrow, and the test will be due midnight Friday as well. So just make sure that you set aside some time to do that. Again, it's going to open at midnight tonight if you want to do it early. If you want to wait until after we review tomorrow, though, that's perfectly fine also. Okay. Any questions, comments, concerns, please let me know. Otherwise, have a great afternoon, and I will see you all tomorrow.